So today we're going to continue with functions and also talk about loops. There's a problem in here, pass by value and pass by reference. These two problems I want to talk about now. In the notes for this this meeting, there's a discussion here about pass by value versus pass by reference. So we could actually look at this. And missing a closing brace there. Got one. There's the other one there. So here's a function called double it. So when we pass in a variable, pass in a value, an integer rather, we pass in an integer x. We multiply that value by 2, and that's it. Then we discard the result. We don't return it. See, this x here, whenever you see a variable with a data type in front of it, like int here, this is a declaration of the, this is where we say that x exists. Now here, this declaration is inside this parameter list for the function. So this declared variable x is visible inside the function only. That's important to keep in mind. This is an issue called scope. That's the scope of x. The scope of x, this x that I have highlighted, is inside the function double it. Here's another declaration of x right there. We also, well, there's something called declaration and definition. This is a definition of x. And the scope of this x is from line 10 down to line 12. And that's it. This x is not visible inside the double it function. They're two different x's, even though we pass it in here. See, when we pass it in here, when we call double it in line 11, a copy is read, so the value, the number stored in x is retrieved. It's a 4. And it's copied into this other x. It's a different x. And this copy then comes into the function. We operate on the copy, and then we return from the function. And then after we return from the function in line 11, we execute line 12. Line 12 is printing this x that's visible inside main, not the x that's inside double it. And so we haven't modified the x that we defined in line 10. So we're going to print 4. Well, there's the 4, but let's make it a little easier to look at. There's the 4. If, on the other hand, we put this ampersand there, now we're saying that x is a reference parameter. We're telling the compiler, don't make a copy of x. Let's operate on the variable that was passed into the function when we invoked it. So this x here, right now, this x refers to this x. They're all the same x now. That's what that ampersand does. It makes it. This is called a reference parameter. So we're like extending. We're extending the scope of x when we call this function doublet. We pass in x to this doublet function. We're extending the scope of x to the body of doublet. So now we're operating on the x that we print here. So when we call doublet, we're going to transform the 4 into an 8. This is a very important thing. I'm going slowly here, and hopefully I'm making a big deal about this because it is. It's not just a big deal in C++, it's a big deal in every language. Every language you work in, you have to be aware of this. It's done differently in the different languages. It's not an ampersand, it's something else, or maybe it is an ampersand. But this concept, this idea of when you pass something into a function, you either pass by value or pass by reference. It's very important. So you always need to be clear about whether something is getting moved as a reference or getting moved as a value. Copied as a reference, copied as a value. And that's it. There's one other thing I could say is sometimes we say const. This is a way of telling the compiler that we're not going to we promise not to modify this x. I'm saying x is going to be treated or should be treated as constant. Of course, here we're assigning to x with the assignment operator, so we're violating that directive or that desire, that statement that x is constant. So this will fail. It will fail to compile, not fail to run, fail to compile. So the compiler says, oh, you can't modify x in line 6, right there, line 6. You can't modify x in line 6 because you declared it const. It's a read-only reference. X is a read-only reference. You're trying to assign to a read-only reference. We can assign to a reference, it just shouldn't be read-only. So const makes it read-only. And that's it for functions. Oh, forward declarations. We cover that. We can organize this code a little differently. We can declare doublet after we declare main. or define doublet after we define main. But this will fail to compile. Because when the compiler reaches line 7, right there, when it reaches line 7, it says doublet was not declared in this scope. Because it's analyzing the code line by line, sequentially. We can still keep the definition of doublet down here, below main. But what we need to do is we need a way, well, and there is a way, we use a way, the following way, to tell the compiler that doublet exists. I'm going to define it later, but now I'm just going to declare it. We call this, declare doublet. And here, this is where we define it. So in line 5, before it appears in main, we're going to say to the compiler, doublet exists. It's a function that is void, doesn't return any value, and it takes a reference to an integer. By the way, the compiler doesn't need that. It doesn't need to know. We call it x. We need the x down here because it's used in the code. But up here, we're just telling the compiler, hey, doublet's a function. It takes a reference to an int, and it returns a void. So this is enough information for the compiler. Except for some reason that didn't work. Oh, I didn't save it. All right. And that's it for functions. Any discussion or question? So you work with these ideas and do the coding, do the practice, and it sinks in, becomes second nature. What about loops? Before I go on, does anybody want me to talk about one or more of the problems that you're working on, perhaps you're stuck on? If somebody has code, we can look at it. I'm going to comment on your code. Anything? Okay. All right. That's good. So there's while loops, do while loops, and for loops. And each one of these loops, any loop written, a while loop can be rewritten to be a do while loop, or rewritten to be a for loop, and vice versa. So you only need one of these type of loops, but just for convenience, the language provides 3 different types of loops. And a loop is something, it means to repeat something over and over again. And this is, this example here, it's called a range-based loop. This is from the new version of C++. I'm not even sure that this compiles. I don't have examples in here of old-fashioned loops. I just have the new style. Let's see if this compiles. No, range-based for loops are not allowed in C++ 98. So that's the version of the compiler that we're using. So what we need to do is tell the system that we want a different version of the standard. I'm trying to remember how to do this. C++ 11. And that took it. C++ 98 doesn't support range-based for loops, but C++ 11 does. So let's look at this. So here we have a string S, and this is the I don't know what you would call this, the control section or something. And then this is the body of the loop here. There's an opening brace, a closing brace, although because there's only one line, that you could actually leave these out. You only need those if there's two or more lines. This statement is glued to that for loop there. But it's most programmers will leave the braces in there because it's safer, because a lot of times you add to the loop, and so you don't have to worry about forgetting to add the braces as well. So what's C? C is a variable here that's declared as a character or a single byte. It's like a byte value. An old character was, 1 byte was used in the past for a character, and not anymore. Now they use 2 or more bytes to represent characters. Because in the past, the language that was supported was English, and then I think some European languages were supported. You could support all the different. You could support the different alphabets using a single byte. But when you get to Chinese and the other languages that have a lot of characters, that 1 byte is not sufficient anymore to represent all of the characters in the alphabet. So you need to use more than 1 byte to represent 1 character. Also, there's character sets that basically, like Unicode, it's a single character set, a single way of representing characters. But you represent all characters in all languages. You don't change character sets and like, oh, I'm going to be in Chinese, I'll use this. I want to be in Japanese, I'll use another character set. No, we just use 1 character set. On the internet, in web pages, and a lot of documents that are passed over the web, what do they use? I forgot what they call it. It's that, I can't remember the name of it now. What's it called? What's it called? What's the character set used on by default on the web? Anybody know the name of it? I should know this. It's my area of expertise. How could I? I'm getting old and I'm forgetting things. It's probably in here somewhere. Oh, UTF-8. There it is. See, char set. Character set is UTF-8. So some characters occupy a single byte, like an English A or B. And other characters, like some Chinese character, would occupy 2 or 3 bytes. And so it's a variable length representation. Unicode is like 16-byte Unicode. That's a fixed length character representation technique where it's always 2 bytes, so you can count things out. But in UTF-8, it's a variable length representation of characters. All right, so anyway, this C is an old-fashioned character, which these days we can think this is just a byte. Okay, it's a byte. And so S is a string, and strings are comprised of characters. So you've got this, and this is an old-fashioned string. I mean, this is a string based on single byte representation. So this S is comprised of these characters, uppercase T, lowercase h, and so on. So what this for loop does is it says, I want to scan through this S here is some kind of a sequence. It's a sequence of characters. And I want to pass through that sequence from first item to next item and so on. We want to go through that sequence, and each pass through the each step in passing through the sequence. At each step in passing through the sequence, this variable C will take on, in this case, the character at that point in the sequence. So first we start with the first character. C becomes the first character, uppercase T, and then we execute the body of the loop. And then C becomes H, and then we execute the body of the loop. Then C becomes I, and then we execute the body of the loop. This is a new style, range-based, of for loops. And so you see, what are we doing? We're just picking out, let me do it like this. I'm going to say hello. It's easier to look at. It prints, for each character that we pull out of the string, we print that character and then we have a new line. So it just gives a vertical display of the string. Let's write this in the way it's in the old way, so that we can compile it using C++98. So this will fail. Let's go ahead and fix this. So in this for loop, the traditional for loop, and this is the for loop you see in lots of languages have the same form. We've got an initialization area that's run once when the loop is first arrived at in execution. And then we have the condition, the loop condition. I'll call it the loop condition. And that's the condition. If the condition is true, we execute the body of the loop. If the condition is false, it means the loop is done, move on, go to the next line in the program. There is no next line, so we just return from name. That's how we terminate a loop. When the loop condition becomes false, the loop is done. Now the loop itself, look at this. This is one statement. That whole thing is a statement. When the statement finishes, we do the next statement. Now it's called a complex statement because it has substatements in it, just like an if statement. This is a substatement. That's also a statement. It's a statement within a statement. So we know this loop statement completes when the loop condition becomes false. And then there's a third section here. It's called the end of loop operation. So 3 areas there. And this for loop usually would declare an integer I. I'll initialize it to 0. But see this string here. This string, these are positions. This is position 0. This uppercase H is at position 0. Lowercase e is at position 1. Position 1 is the second position. You got to get used to that. Normally, in computer languages, counting starts at 0. Because in the hardware, counting starts at 0. The computer starts counting from 0. If I was going to count the people in this room, I would start 1, 2, 3. I would start at 1, right? That's how humans start at 1 when they count. But computers start at 0. When the computer looks at this classroom and they want to count the people in here, they're going to go 0, 1, 2, 3. And they're going to end 4, 5, 6. They end at 6. So there's 7 students. See that? Because you started at 0 and you ended at 6. That means you got 7 things. And that's how the computer works. You're going to have to make that shift. So you got to sort of practice that. So I is going to be used to represent the position in the string S. So when I is 0, it's pointing to that uppercase H, the first character. When I becomes 1, it's pointing to the second character, the lowercase e. All right. And now we want I to go from, let's see, 0, 1, 2, 3, 4. We want the body of the loop to run when I equals 4. But we don't want it to run when I is 5, because when I is 5, there's nothing in position 5. There's an O in position 4, but nothing in position 5. So we want I to be less than 5. So as long as I is less than 5, I make sense to use as an index into the string. Once I hits 5, it no longer corresponds to a character position in the string. There's no position 5 in this string. Now, so for each I, we're going to run something here. So at the end of the loop, we're going to increment I, because we want to go to the next character. So we start with I0, then we want to go to I1, then I2, I3, I4, and then we want I to hit 5, but when I hits 5, at the end of the loop condition becomes false, and we're finished executing the loop statement. And we go on to the next statement in the program. Now, how do we access the character at position I? We want to print the character at position I. We could use this notation. That's the character at position I. So we're going to see other sequences in this course, arrays and vectors. They use exactly the same notation. These are brackets, square brackets. I put this S represents a sequence of things. And then we have a value inside square brackets following that name of it, the sequence name. We got the value in the square brackets that represents the position in the sequence, the position I in the sequence of characters S. Let's check to see if we got this. It compiles this time, and it runs exactly the same. So this is using an older form of the for loop, which is the predominant form, by the way. Most times you're going to see it like this. And once again, this is the initialization section. This is done only once before anything else is done in the for loop. This thing, when the for loop begins to execute, this statement, this operation will perform first and only once. Then we're going to move on. After that's performed, we check the loop condition. If the loop condition is true, then we do the substatements. After we do the substatements, we do the end of loop operation, which in this case is to increment I. Add 1 to I. After we add 1 to I, what do we do next? Anybody know? I know it's getting boring here. Check the loop condition. So it says loop condition, substatements, end of loop operation. Loop condition, substatements, end of loop operation. And you stop when the loop condition is false. So 1, 2, 3. That's the pattern. It's first you do the init, and then you do the loop condition, then you do the substatements, then you do the end of loop operation. Maybe I think that needs hyphens, I'm not sure. And then after you do the end of loop operation, you come back and do the loop condition again. I never did this before. It's my first time doing a graphic for this. Oh, look, watch this. I learned something new just now. How's that? This shows the flow. Yeah, that's nice. So you do the initialization of the loop. That's here. And then once you do that, you get into this sequence of three things that happen one after another. Check the loop condition, do the substatements, do the end of loop operation. Oh, this is not right. Sorry. Good thing I looked at that. This should go down. I have no down thing. All right. So I don't have a down arrow. But after the end of loop operation, we come back and check the loop condition again.
You can use the V too.
Huh? Hey, that's a great idea. Let me see. Wow, that's a cool idea. Uppercase V or lowercase v? Lower. Wow, that works. Incredible. Good idea. Huh. So now the loop condition is the thing that can break this. So once the loop condition is false, then we're going to exit. I'll go ahead and do this. Why not? So the loop condition, when the loop condition is false, we'll exit. And when the loop condition is true, and it's not quite working the way I wanted it to there, when the loop condition is false, we exit. And when the loop condition is true, we go forward. There's a diagram. All right. Let's hold on to this. Maybe I'll add that to the notes. And like I said before, there's different forms of loops. See, these are the old loops. Actually, this is a range-based for loop, and I just showed you the non-range-based for loop, which is the traditional for loop. What about the while loop? Let's reconfigure this loop as a while loop. And a while loop lets us repeat things, just like a for loop. We say while, and here we have the condition. We just have the condition, like that. So if the condition is true, like that, it'll keep repeating the substatements forever. Condition never becomes false. We just pass in a hard code true in there. So this is called an infinite loop. So we need a way to exit this loop. After we'll need to, before we enter the loop, in this particular situation, we need a variable I that's going to be used to index into the string S. And after we use it, here in line 11, to access the character at position I, then in the next line, we'll increment it. So that gets us ready to access the next character. But we don't want to go too far. We only want to do this while I is less than 5, because when I hits 5, we're past the end of the string. This is how the loop looks as a while loop. That statement up there, so the while loop we just looked at is equivalent to this. So the while loop is more primitive. While loop, it doesn't have an initialization section. It doesn't have an end of loop operation. All it has is a condition. When the condition is true, repeat the substatements. See, I like while loops more than for loops, actually, because they're simple. When the condition is true, run the substatements, and then repeat. So the only way to break out of that loop is if the substatements do something that can render the condition false. Otherwise, you're stuck in an infinite loop. Let's test, make sure we got this. Works. Now, there's another way to break out of a while loop. We use the break statement. We can make it an infinite loop. And then we can use a condition like if I is greater than or equal to 5, then break. Break means exit the loop. This will work too. So we keep the loop condition simple, just it's true. And then inside the loop, we have some logic here that decides whether to break the loop or not. What happens if we made this an infinite loop? I'm doing this at some risk here because I'm on cloud 9 and it's going to lock up the terminal probably. What happens if I just let it go forever? What's going to happen? It's going to try to access memory, starting at, S, and it's going to run past the end, and it's going to keep trying to access new bytes of memory. And it'll get to a certain point where it violates some kind of constraint that the operating system has put on the process. So we get like a memory error. Let's see how it works. Not yet. Bad. See, the problem is we're on cloud 9. That's the problem here. Oh, there it is. Segmentation fault. It worked. See, there was a lot of output. And if I was running this on my local machine, it would say segmentation fault right away. But because we're executing on a virtual machine over the internet, all of the blank lines have to be transported to us over the network. So we're spending a lot of time receiving characters from a remote location. That's why it took so long, I think. That's my hypothesis. So what about the do while loop? The do while loop looks like this. Let me put this back in here. If I is greater than or equal to 5, then break. I don't need braces there because it's just a single line operation. It's a single substatement. This break by itself, that's a complete statement. It's a substatement of the if statement. I don't need to use braces when it's just one substatement. But this is a little easier to read, perhaps. Let's check and make sure I got that right. What about as a do-while? So in a do-while loop looks like this. So do the following lines while I is less than 5. So it's just another way of doing the same thing. Oh, forgot the semicolon. One of the reasons you would use a do-while loop is it always runs the substatements once. As the loop condition is not evaluated until the substatements are first run. So you'll always get at least one execution of the substatements. So in some situations, that's nice to have. Now, once again, you don't have to use any of these three loop forms of loop. They're all equivalent to each other. You can always convert code from one type of loop to another. Yeah.
So could you do while, like just keep continuing with like a bunch of whiles?
Add more whiles.
Yeah. Like instead of do if else and then
The answer is no. Probably it's no. When you have loops that work together, normally you have loops within loops. I don't know, whatever. It's just something like this. You'll have a loop that's nested inside of another loop. That's how you see loops together. They're either nested or they're done in parallel. Not in parallel, in sequence. This is done in parallel, I guess. And this, you have to watch out when you start nesting loops. If you have, that's where the number of computations starts to get large. Okay. So if your outer loop runs n times, and for each pass of your outer loop, if your inner loop also runs n times, then you have n times n executions of the innermost substatements. So n squared. So then this is where you start to notice performance issues come up in code when you start nesting loops, if you have long sequences. I should have put in this page here all of the alternatives. Maybe I'll do that later. All the alternatives that we looked at. I should put those in there. There's also continue statements. It means not restart the loop, but go back to the top of the loop and run it again. You starting with the loop condition. So I'm going to skip that, but that maybe at some point, if we need that, I'll bring that in. You might want to read about that continue statements. We might not need it, so I don't want to talk about it now. So that's it for loops. And then we have this assignment on loops. Let's look at some of the problems. Here's the first exercise on for loops. Write a C++ program that prints every integer between 330 and 550. So you're going to want to print 330 inclusive. That means include 330 and include 550. So you're going to want to print 330, then 331, then 332. So you don't want to have, 220, cout statements in your code, with a different number in each line. You'll use a loop. So you have a counter like I. I is a nice counter for integers because I sounds like an integer. And you initialize I to 330, print I, and then let I increment to 331. And then print it again, and then increment I to 332, print it. You see the repetition there. And then when I hits 551, then the loop condition's false, and you're done. You don't do any more printing. But you have to let I hit 551. You have to let it hit 551 to make the condition false, then to terminate the loop. And lots of other problems in here. 6 and some exercises. You can't do much without loops. And so at this point in the course, we've got loops and if statements and functions. So that's a lot. You can do a lot with that. But if you're missing any one of those three, you can't do much. See, we could stop with that, and we could just write all kinds of code now, just with what we've learned at this point. We don't have to study classes. Or the classes. Or other elements of the language. These are the core features: functions, loops, if statements. All right, what about coming back to looking at conditions? Everybody's getting this? This is due, right? On Friday. I think we covered random numbers last time. If-else statements. But that's due. Is that due this Friday? Or was this due already? This is due this Friday.
Yeah. Can you go over the modulo thing?
Modulo?
Yeah.
Yeah.
I'm not really sure how that works.
Okay, we'll do this. What's 5 mod 2? Oh, what am I talking about? Oh, divide 5 by 2. Take out as many 2's as you can, and then give me the remainder. So you can also call this the remainder operator. Modulo operator, remainder operator. Give me the remainder after doing this division. Take 5, divide it into groups of 2, and give me the remainder. There's going to be some remaining amount that isn't groupable and it isn't placed in a group of 2. It's called a remainder. So if we did 11 mod 3, it's like take 11 and divide 11 into groups of 3, right? Divide 11 by 3, divide it, put it into groups of 3. Well, I can only get 3 groups of 3. And then I have 2 left over. Okay? So 11 divided by 3 is 9 2/3. What's the 2 over the 3? I say 11 divided by 3. I'm sorry, it's 3 2/3. So I can take 9. I can take 3 3's out of 11. That's 9. And if I take 9 out of 11, I get 2 left over. Right? That's smaller than 3, the divisor. So that's the remainder. You got to think over to practice this a bit. This is pretty important, actually. for the math majors here, this is also important, modulo. Now, let's look at one thing we can do with this. Let's suppose we input a number, n. We're going to input a number n, and then we're going to say, we're going to have some code in here, decide if n is prime. And we're going to say, we'll have a Boolean variable here. Let's create a Boolean variable. We're going to call it is prime. And I'll set it to true. And then we're going to do something. And then when we're done doing something, we're going to examine n. We're going to assume that n is prime. We're going to assume that n is prime. And we'll have a variable to represent that. N is prime. Let's assume n is prime. We're going to do something. Oh, well, look, see if, we're going to, try to find a divisor of n. If found, then set n is prime to false. So we have this initial assumption, which is codified, if that's the right word, as a Boolean variable set to true. So we're going to assume that n is prime. If we find a divisor of n, then we're going to change this Boolean variable n is prime. We're going to change it to false. And then at the end of the program, we're going to examine this Boolean variable. If n is prime, we're going to say prime. Else we're going to say not prime. Okay. Let's see how that would run. So we're going to write this program, n. So we're going to enter in the number 7. I know that's prime. Enter it in there, and then the program says n is prime. I put in a 2. It says n is prime. Maybe we say n is prime. Okay, we'll do it like that. N is prime. N is not prime. So 11, n is prime. 6, n is prime. Oh, we got it wrong there, right? So we want to say n is not prime. So we make this assumption that n is prime. And now what we want to do is try to divide this n by a whole bunch of numbers and find a number find one number that evenly divides into n. And then we're going to change our assumption about this, about the number. We're going to set this Boolean variable to false. So we need to try things. So we've got to do it like this. So if n mod 2 is 0, that means n is evenly divisible by 2. So we set n is prime to false. But what about 9? 9's not going to work, right? So we got to find 9. We got to divide by 3. We're going to say, oh, no, 2 does not evenly divide into 9. Well, let's try 3 in that case. And 3 evenly divides into 9, and so we catch it, see. So whatever n is, we have to try dividing all of the we have to try dividing n by all of the prime numbers less than n. We're going to take, well, what happens if n is 25? 25 is not prime, but 2 does not divide into 25. 3 does not divide into 25 evenly, but 5 does. See, so what we're going to do is just sort of carry on this, and the next number we would have to try is here is 7. I have to keep going forever. So this code is good for small numbers. So 25, not prime. And what about 6? Not prime. Can anyone give me a number where this is going to fail? Huh?
1.
1? No, we're going to leave 1 out. 1 out. I'm not going to consider 1. Let's forget about it. It's going to be bigger than 2. Give me a number bigger than 2 that this program is going to fail on.
11.
You can calculate it. What's the next prime number after 7? 11, right? Did I get that right? So what's 11 times 11? I don't know what it is. Is it 121 or something like that? 121, right? Did I get that right? So it says 121 is prime, but that's 121 is 11 times 11. So that's because, our procedure here is only going to be good for small numbers, right? We can only go so far, and then we got to start. We have to know, what the next prime number is. Well, the next one will be 13, and so on. So we need a loop here. This divisor, we're going to have a divisor, call it I. We'll start at 2. And I is going to be less than n. We don't need to go past n. We're going to increment I. And this I, if n mod I is 0, then n is prime, set to false. See that? Now this code divides by all values less than n. So that we got to put a 4 in there, right? And then after the 5 we try 6. But it may be wasteful to do this. But we don't check here. I'm not checking that I is prime. See, I'm just going through all of them, and that's okay. So here. See, n will not be divisible by 4 because we already checked to see if n is divisible by 4, it'll certainly be divisible by 2, which means we would have caught it at this point. See, so this doesn't hurt us. It's kind of redundant, right? So we're going to leave those out. So now we have a simple loop. So now we can get big numbers. 121. 121 is not prime. 66893. Do you believe that's not prime? 66891. Not prime. You know, we got to find a prime number there, right? What that one? Well, it can't end with a 5, right? It should end with something like a 3. Well, that's too big, isn't it? See, we're in a loop that's going to run too long. Yep, that one's too big. Oh, look at that, it completed. I don't believe it. That's a prime number. What do you know? Anyway, running out of time now. We could be a little bit more efficient here. Like if we find a divisor at this point, we can break from the loop. That's a little better, right? We don't have to keep trying the numbers, so we're going to break from the loop. So that'll work. That'll run a little faster. Well, not the one that we just did, but on others. That one went pretty fast, not prime. Well, that hit it right at 5, right? Watch this. I have this giant number, end with a 2. That's not divisible by 2? Isn't everything that ends with a 2 divisible by 2? It is, right? Why is that taking so long? Did I compile? I did. I don't get it. Why is that taking that long? Oh, its n is prime. What's wrong with that? Can a number that ends with a 2 be prime? It can't, right? Can you always divide a number by 2 when it ends with 2? So you guys got to help me out here. Is that right? Do you know a prime number that ends with 2? Nobody knows this stuff, huh? List of prime numbers. You see any numbers that end with 2? So we got something wrong. Why does it say that this, oh, I know why. The number's too big. This exceeds the an int. So the max int, look at this. It's too big. Let me show you. What is the largest possible integer? Well, there's a header file called limits. See, we're entering in a number that's too big, and so actually this number, it read, I think it just read part of it, see? Maybe it ended with the 3, and it chopped to 422. Something happened like that. Because we entered the number is too big. All right, what's the max int? Int max, there it is. int max is not declared in this scope. Or limits.h. Is that it? Oh, that's not right. Int max is not declared. Well, I guess that was it. This is the maximum value. This is bigger than that. You see that? So that number we entered in there, we lost, we were just by, it looked pretty close to this one. Let's go ahead and use the maximum value. Let's put in the maximum value. I think that's a prime number. Let's see. Running out of time. The maximum int on this machine is a prime number. Anyway, that's what was going on with that. And we'd have to do some error checking to see that the user entered in a number that fit into memory. Yeah?
Does it have to be an int, or can you use a float?
You can't use a float. It has to use it has to be an integer number. But you can increase the size of the int. If I just said long int here, see? And now we can fit a bigger number. Now that's 8 bytes instead of 4. And that would be a long max. Here's a long max. So the number that we entered in before will work in this case. But I'm not going to do it because it probably won't terminate. On the other hand, if we make it a little faster, like this n here, there's no reason to go past n squared. I mean square root of n. So we can do this. Now, square root of n is probably not defined. So what we need to do is get a header for that, called cmath. And this, now that we have it, we've got a bigger maximum, but now we're stopping at square root of n. Let's see if we can get a different result. This is the number that we, what the heck? Someone connect? No. What just happened at the terminal there? Oh, I just messed it up. I really wanted to get that. Let's see the command line. No, it's crashed on me here. I don't know where this came from. I wanted to retrieve that old number, but all right, forget it. Anyway, running out of time. This is, here's an example of using loops and using the modulo operator. That was the question about mod. And this code here about checking for prime numbers, this will come up several times in the future problems. So that's another reason I talked about it today. So this algorithm to determine if a number is prime or not, we're going to be using that in several problems, and it's going to appear on an exam. All right, so a quiz in the final exam. So you need to know that. Is that enough for today? Any more questions? No. Yeah, question.
You try about doing some activity 3 functions on exercise 4.
Assignment 3. Assignment 3, exercise 4. Strings. You want to see this, people? Everybody's all right? Right. Let me, do you have a solution? Do you want to look at your code? You don't have anything? So let me show you this. So we have to find the initials of your name, right? That when you enter it in there. So if we have a string, I'm just going to make this fast. You know, here's a string, and I want to I better use a different. Alice Smith, okay? Let's just you just use the use the substring function. Actually, you don't need the substring function. You can use what we looked at earlier today. You can use the index function. So this will display the first character of the string S. See that? And if you have two strings, S and T, you can just you know, print the first character of each one. So you don't need the substring function, but I'll show you how to do it with the substring function as well. There's the initials, AS. But the substring function would look like this. It's the character at position 0, and we want one character starting at position 0. That'll give us the A, uppercase A. I was thinking you would solve the problem using substrings as opposed to using the index operator. But you can use the index operator or substrings for this particular problem. The substring is more powerful because your substring, this returns a string of size 1. This returns a character. So you're going to, this is a bit more flexible. Like if I want 3 characters starting at position 0. Alley, right? And how about 3 characters starting at position 2? What's that going to be? What's it going to say? This is like a quiz question, okay? What's it going to say? Anybody know? Huh? Ice. Because this, I wanted you to think about this to remember that counting starts at 0. This is position 2. The third position is position 2. So we're going to start the substring at position 2. That's the third position because counting starts at 0. You know, A is 0. L is 1. I is 2. It's position 2. And then we want 3 characters starting at position 2. I, C, E.